Hi there, it's Advanced SQL time again, and I welcome you back to the next chapter of our Advanced SQL exploration. It's chapter 4 now, and the title would be Arrays and User-Defined Functions. We will start our discussion with arrays. So the prominent collection data type that you know from all of your programming languages is also present in PostgreSQL and in many SQL dialects. And we will not use arrays as a replacement for tables. Tables still play the primary role in relational database systems, but arrays may be used as the contents of table cells. And as such, they play a really prominent and very elegant and very efficient role in the representation of complex data inside a relational database system. So let's see what's going on here. Okay, so you could say that arrays are in some sense alien to the relational database idea. Relational databases are about tables that contain rows. Tables are unordered data structures, and that's just the antithesis to arrays, which are the primary ordered data structure out there that you will probably think of first when you think about any order in a data structure. And as such, these two models, tables and arrays, seem to be counterparts, but as you will see, arrays are very neatly integrated into SQL and in PostgreSQL in this particular case. We have to recall that our primary aim in modeling simple relational tables was to the preservation of the first normal form. So all the values v that you would store in such a table cell are considered atomic. Atomic with respect to the tabular data model, with respect to the relational data model. There is no tabular structure in this cell value v. And indeed, arrays do not provide relational or tabular structure. They are their own data type with their own operations. So although we will be able to store a number of elements, say the elements x1 to xn in one single array value, this would not violate first normal form. We would be able to access the elements x1 to xn individually as you would expect from an array data type, but we would not use the concepts and the operations of the relational data model. We would use particular array functions and array operators that we will of course discuss in the upcoming videos and in the next few minutes. So this is a possibility to store structured ordered values inside table cells, but it's not in violation of the first normal form, because these are really two separate worlds, the tabular world and the array world. There is very well-defined and quite elegant bridges that lead you from one world to the other, but at any point in time you will be clear about in which world you are operating in and which operations are currently the operations to use. Okay. You've already seen that I was using this particular notation to denote an array value of n elements x1 to xn. So that's a bit of a sad story. The array data type is the one, the role model positionally indexed ordered data type supported by the PostgreSQL data type system. But the PostgreSQL developers decided to use braces, these set-like braces, to denote this ordered data type. So when you see arrays output, for example, in the listing of tables, we will see this in a minute. If you see such arrays output in the PostgreSQL console, then you will see such arrays denoted by curly braces, which of course to virtually anyone on this planet suggests that this is a set of values which would be intrinsically unordered. But no, this is the notation chosen by the PostgreSQL folks to denote arrays. It's an unlucky choice at best, and my proposal would be those who have decided to take this particular notation, no dessert for you today. Okay, so with that out of the way, let's see how arrays inside tables taste. So for each type tau, for almost any type tau inside the PostgreSQL type system, there would also be the type tau array, tau square brackets, or alternatively denoted tau suffix array here. We will almost always use this notation. I think exclusively we will use this bracket notation. This is the type of homogeneous arrays of elements of tau. All elements inside such an array are of type tau. No mixed contents, no mixed element type contents inside such an array. Tau may be almost arbitrary. So for sure, all of the built-in types that you are thinking of now, like booleans, integers, text, those may be elements of an array. Also, user-defined types like the enums that we have defined, or the row types that we have defined with create type, for example, those might be the element type tau, and an array of row types, of row values, in fact, would come already quite close to a table if you think about it. But caveat again, arrays of, even if there are arrays of rows, are no replacement for the tables that we are working with in relational database system. The support, the scalable support for tables of rows is significantly more prominent, significantly more efficient inside relational database system than arrays of rows, for example, than for arrays of rows. So although PostgreSQL and many SQL dialects support arrays, they are not array database systems or array programming languages in any sense. It's really the table that remains, that takes the center role here and remains in focus. Okay, so if you talk about such array types, you may be used in some programming language to talk about arrays of a fixed size of n elements, for example. You could use this notation in PostgreSQL, but the n would be ignored. Arrays are dynamically sized and shrink and grow as needed when you append further elements, for example, to an array. All right. So this could be the contents of a particular table T. It would have multiple columns, and one of these columns might be of type integer array, this column A here. And the contents of that column would, of course, be integer arrays. As you can see, all of the arrays in this column must be integer arrays. We are still in the relational data model, and in the relational data model, all values in a column are of the same type, for example, integer arrays. And inside these arrays, all of the elements inside the arrays will be integers. So these are homogeneous arrays that we are talking about. If somebody would take arrays away from us now, that would be sad, but it would not actually be a disaster. But we could always simulate the semantics of arrays with our already given table constructions. Okay, so if we had to simulate that table T you've just seen on the previous slide, the 3-column table T with column A that was storing integer arrays, 4 different integer arrays, then a purely relational representation of the same information content could be devised in many ways, but this modeling of the information that you see on this slide using 2 tables would be one option to model the same information. All right, so we would of course have our table T. It would have many columns, but one of the columns would be would be holding the arrays, namely the column A. Column A would be of some type kappa here, some surrogate type, some reasonable key type. So all of the values that you see here, the alpha I, are in fact key values that reference a different table, this table in which we would indeed store the elements of all of these tau arrays, tau typed arrays. All right. So for example, let's switch back one slide and look at the second array stored here with elements 30, 20, 10. Okay, so 30, 20, 10 would be represented by this key value, by the surrogate value alpha 2. And if we look alpha 2 inside this array table, our array contents table in a sense, then we would find 3 entries of alpha 2 here, representing the 3 elements stored inside this array, 30, 20, 10, as expected. All right. We would also have information, explicitly encoded information about the array position of 30, 20, 10, which would be found at array indices 1, 2, and 3 here. Okay. You could see that array 4, the last array in the table in table T, would have only one element with only carrying a null. Again, array A alpha 1 would have 3 elements, and array alpha 3, if you recall, switching back again, would have no elements. This would be the notation for the empty array of no elements. And the representation of the empty array in this alternative purely relational modeling of the same thing would be encoded by the absence of the key value, of the associated key value alpha 3. It's present here in the T table, but it's not to be found in this particular column, which encodes no elements, which encodes the empty array. The array associated with the surrogate or key value alpha 3 would be considered empty. Okay, now you see why it's vital that all of the elements inside such an array are homogeneous. This enables us to model the contents of these arrays all in one collected element column here in this representation. Okay, so if arrays would be gone, that would be sad, but we would be able to model them purely relational as in this as on this slide. What the slide also shows is that the index type that we're using, the positional indexes that we're using inside such arrays are of type integer. That's the same as for PostgreSQL arrays. And they are one-based. And again, this is the convention that is used in PostgreSQL arrays. The leftmost element, the first element, is living at array index 1. Okay. So how would you specify, how would you give an array value and include it in a particular query? You would be required to denote array literals or array constants. So values of type tau array for some type tau. And the convention, there's 2 conventions actually inside PostgreSQL that will allow you to do that. Only one of these conventions will be actually used by us. And it's the one using this explicit array keyword here, or the array constructor. Empty arrays in that notation would just list between square brackets the empty list of elements. So that would be the empty array, because this empty array is really polymorphic. It could be an empty array of booleans, an empty array of integers. You cannot tell. You always have to typecast. You always have to typecast such an empty array to the desired element type that you are seeing here, as you can see here on the slide. So that would be the empty array of tau elements. Okay. The non-empty array would use a very similar notation, but between square brackets we would just enumerate all the n elements of this non-empty array. All of the xi here have to be of type tau. We are talking homogeneous arrays here. Okay. And of course the order is very important. This is the first element, this is the last element. This would live at index 1, this xn would live at index n as expected. The alternative notation that we won't use much or won't use at all actually in this particular course is the brace-based notation. The brace-based notation that would rely on the textual representation that is so common in the PostgreSQL literal notation. And we would need to cast this particular value to a tau array to ensure that this string is indeed interpreted internally as an array of tau values. All of the xi have to be of type tau, also in this case. This would be a notation for one-dimensional arrays. So all of the array elements live in one sequence in one dimension that can index with a single integer inside this array. Multidimensional arrays or array literals of this particular type, this would be a two-dimensional array, and you can probably also see how 3 or 4 or more dimensional arrays would be denoted. They use the nested array constructor notation that we will also use in this course. Nested arrays will not pop up that much, but we could use them and we could specify literals of them in this particular notation. All of the elements of such a multidimensional arrays would be arrays themselves, the row arrays. So what you see here specified is actually a rectangular array that would be indexed like this. So all of the rows have n elements here, all of the rows, and this is no coincidence. We can only talk of multidimensional arrays in PostgreSQL if these are completely rectangular. If one row has n elements, all of the rows have to have n elements. All right, so these would be the n rows. Here's one of these rows, the first row. And the outer array constructor would just enumerate the k rows of this multidimensional array. So the outer constructor would represent the vertical dimension, the second dimension here of this particular array. Okay. Again, we could use the nested braces notation to specify the same thing, but as we said, this is not used much in this lecture. Okay. So what would be one example? Could be one example of such a use of arrays inside tables? One example use might be the representation of yet another data structure inside tables, trees, for example. So this slide proposes an array-based representation of trees, of forests even, of set of trees. As you can see, T3 actually represents a set of 2 trees, a forest. And such an encoding of such trees or forests using arrays could look like it's proposed here in table trees. Each of these rows, each of these 3 rows would represent a single forest. You see that the T1 and the T2 forest are indeed single trees only, but T3 is indeed a forest of 2 trees. So each of these 3 rows would represent a single forest. All right. We would have additional meta information that would characterize these trees, add properties to them, or maybe are only used to identify them. That would be this particular column tree here that we are populating with some unique identifier that allows us to identify and extract one particular forest out of this table. Okay, inside the arrays here, you would find parent information and label information, for example, for all of the nodes of these trees. So if you are looking closer here, the T1 tree has exactly 6 nodes. They are numbered 1, 2, 3, 4, 5, 6. So exactly 6 nodes. For each of these 6 nodes, we would save parent information. Which node is my parent? So that would be stored in this particular array. The node at index I, at index 1, for example, would represent the parent of node 1. Since this is the root of this particular tree, there is no parent, and the parent of the root would be null. All right, but here at index 2, let me point at that and maybe be more specific here. The element at index 2 has a parent that is node 1, and that is exactly what we are seeing here in this depiction of the tree. The node at index 2 has as its parent the node 1. Okay, and this is what is recorded in this parents array. So each of the nodes of this tree, 6 in the case of T1, have their own entry in this parents array. And the same organization is used in this labels array. Each of the nodes, numbered from 1 to 6, would have their label, their node label represented here inside the labels array. You see that I have denoted the labels of these nodes in a separate tiny tree or forest picture just next to the tree themselves. Otherwise, the notation would be very cluttered here. Okay, so for example, this last node, the node number 6, has been assigned label F, as we can see. Okay, so index 1, 2, 3, 4, 5, 6, the last node indeed has label F, as we can see here. This is a very extensible encoding of trees, because if we later see that our nodes need more properties, like for example weights or something, anything is possible here, we would just be able to add more columns to this trees table. Each of these columns would live arrays of length 6 in the case of T1, to assign that particular property a weight, for example, using an array of length 6. Okay. You can see that in this, in the case of the T3 forest, there is indeed 2 root nodes recorded in the array encoding, the node number 1 and the node number 3. They both are roots because they have null parents, and that's indeed the case. 1 and 3 are roots in this particular forest. So that would be a very simple encoding of trees using ordered arrays. And you can see that using an ordered data structure really is important here, because we have to be sure that order is respected inside these arrays. This is the label information for the first node. It has to coincide with the parent information of the first node. So corresponding indexes in this array and in this array regard the same node, and order in this representation is really vital. Okay, that's nice. Let's switch over to the editor indeed, and I brought PostgreSQL with me, and of course we could create this trees table inside our live PostgreSQL instance too. You see that I've decided to identify the trees of my example using integer primary keys, and then would only store the parents and labels information as on the slide. And both the parents and the labels would be represented in terms of arrays, in terms of int arrays, or in terms of text arrays when it comes to the storage of textual label information for each of the nodes. So let's do that. Let's create that. And then let's populate the tree. And you can see the syntax I'm using here. Of course, I need to specify array literals now that I'm trying to insert rows into my tree table. And as I promised, I'm using this array constructor-based notation instead of the braces-based notation. That will be the common case in this particular lecture and course. Okay, so this is the array of parents. This is the array of labels for the first tree, T1, which is represented by integer key 1 here. You can see that I'm doing this for all the 3 forests to be inserted. Here's the 2 root nodes that are, or the 2 null parents of our true root nodes. 2 root nodes, okay. And here you can see that there's other ways to convert data into corresponding array values, and I think this should be almost self-documenting. This is a string to array function which you could specify a string representations of elements. This string would be divided into individual elements at this particular separator character or symbol, the semicolon in this case, and this string would be split up into 5 textual labels, into an array of 5 textual values. This is exactly what we are required in this row 3, where there are 5 nodes to be specified. Okay, we will learn more and see more ways to convert other data, tables for example, into arrays, but this is something for the upcoming videos. So let's insert this these 3 rows to populate the trees table, and then look at the trees table and to see the brace-based notation of PostgreSQL in all its glory. All right, so 3 trees or 3 forests represented in the trees table. Okay, this is the labeled arrays, for example. You see gloriously used brace or set notation to indicate this ordered array of textual values. All right. Okay, now that we are this far, we can start to do cool stuff with arrays, operate over them, and marry them with data that is living in other tables, for example. So the interoperation between arrays and tables really is the spice in the mix here. And to see how this goes, I invite you to stay tuned for the upcoming videos. Until then, take care and bye-bye.